Alright, in this lesson we'll look back at the slope of a tangent line, and earlier in the year when we estimated the slope of a tangent line, we would just sketch it and then try to find a point on the estimate the coordinates of a point on the line. So we know this point, and we'd find another one. We can estimate the slope, or we might even look at it and say it looks like it's a slope of 1. So here with this function 1/2 x squared, we're going over 1 up 1/2, over 2 up 2, over 3 up 4.5. And in this lesson we're going to find the exact slope of the tangent line using a limit. And so here's the process. Here's the same graph. We have the same points. We're trying to find the slope of the tangent line here. And to do that, we're going to find the slopes of secant lines. So we'll just say the red line is maybe close to the slope of the black line. And we can find the slope of the red line because we have 2 points. So we have the slope of the red line is, and that's called a secant line, (3 minus 1). So we'll say the slope of the black line is close to 2. But then we can get closer than that, and we'll have, let's draw another secant line from that point to that point, and now we'll say the slope of the green line is 2 minus 1/2 and 2 minus 1. And now we can say, well, the slope of the tangent line is close to 1.5. And we can see that the green line is closer to the slope of the black line than the red line. So as we move these points down the graph, we're moving these x values in, we're getting closer to the slope of the tangent line. So we could even go closer. This is, so why don't we try 1.5? On the curve, and we would have that one. So we have the slope of that point at 1.5. We're going to have f of 1.5 minus f of 1 divided by 1.5 minus 1. And that's going to be 1.25. So we have f of x is 1/2 x squared. And as we move closer and closer to 1, as the x value approaches 1, the slope is approaching the actual slope of the tangent line. We can get closer. Let's make a table. Alright, so what's happening here is I'm choosing x values that are getting closer to 1. Just like I was doing up here, we have started with 3, we found a slope. Let's move it in closer to a 2. Let's use the coordinates at 2 to find the slope and now it's 1.5. Let's go in, x is 1.5, and now we have a slope of 1.25. Let's go all the way to 1.1, and now we have a slope of 1.05. Let's go to 1.01, and now we have a slope of 1.005. And we can see we have a limit here. The x values are approaching 1, and the slope is approaching 1. So that's how we can use a limit to find the exact slope of a tangent line. And we just need to set up, we have two ways of setting up the variables. We have to generalize, because here we have a specific function and we have specific x values, but we need to make this general for any function. So this will be any function, and we want the slope of the tangent line at x. So then we need to start some distance away from x. That distance is delta x. So this x value is x plus delta x. And then this y value is f of x plus delta x. This y value is f of x. So with this setup, we'll just find the slope of a secant line, find the slope of the secant line, and then let delta x go to 0. And if delta x is 0, we'll be back at x. So we have to find the slope of the secant line. The slope of the secant line is just going to be y2 minus y1 over x2 minus x1. The same formula we always use for slope. And in this case, y2 is f of x plus x, f of x plus delta x minus f of x. So that's y2 is f of x plus delta x, and y1 is f of x. And then we just have x2, x plus delta x minus x. X minus x is 0, and we just have delta x. Alright, that's the slope of a secant line. So then the slope of a tangent line is just going to be the limit as delta x goes to 0 of this difference quotient. They call it a difference quotient because we have two differences. Alright, and sometimes we get tired of writing delta x, so we could also write it as, a lot of times they'll say h. They'll use h. So now we have f of x plus h minus f of x over h. We can have it with a delta x, we can have it with using h. It doesn't matter. We can also use a different setup, and this is a little limited. We can't do one-sided limits or we can't do the slope at the end of at an endpoint, but over here we can. So we just set it up a little differently. We have the same formula. The slope of the secant line is y2 minus y1, x2 minus x1. y2 is f of x, and y1 is f of a, and then x minus a. That's the slope of the secant line. So then if we want the slope of the tangent line, we want to find the limit as a goes to x. as x goes to a, and that will give us the slope at a. So we want the slope. The process is the same in this picture. We start with a secant line going all the way out to some point over here. We want this x value to work its way back towards a, and that's what this is saying. X approaches a, and then this slope will approach the slope of the tangent line. And now we just have a lot of algebra to deal with. Remember that slope of the tangent line is the same as saying derivative. Derivative is the slope of the tangent line. So f prime of x is the limit as h goes to 0 of f of x plus h minus f of x over h. So we can, if we're going to use this formula, we just copy the formula and now start substituting and simplifying. And a safe way to do that is to say that this is f of x plus h, this is f of x, just so that we don't forget to include anything. And now we have to put in f. Well, that's 5 minus something squared on both of them. F is always the same. And then here the argument is x plus h. And here the argument is x. So we have to expand this. Distribute negative. And we have 5 minus 5. So that adds up to 0. We have positive x squared, negative x squared. Those are 0. And we have this left over. So let's factor an h out of both of these. So we took an h out of both. H's cancel. And we want the limit as h goes to 0. Well, as h goes to 0, it will be a 0. As h goes to 0, x stays the same. So we have a 1 in the denominator, and then h goes to 0, so we just have negative 2x. And the question did want the slope at 2, 1. So we'll say that f prime of 2 equals negative 4. And also remember that in the power rule, without using a limit, we can do the derivative just with the power rule. The derivative of the 5 is 0, and the derivative of x squared is 2x. So we can always check that we did everything correctly. right, pause the video and try this one. We want f prime of t. That's going to be the limit as h goes to 0 of f of t plus h minus f of t over h. So we have two big spaces for the function, and let's have this f be here. That's something squared plus 3. Something squared plus 3. There's another f there, so that's also something squared plus 3. And in this function, the argument is t plus h. In this function, the argument is t. So we'll expand that. And remember, when we're expanding that, we have to do FOIL, and it would be th, th, t squared, th, th, h squared. And this is where we're getting the 2th. All right, we have a negative t squared, positive t squared, negative 3, positive 3, and all that's left are two terms with factors of h. So we'll factor out an h. And it cancels. So now we have the limit as h goes to 0, 2t plus h, and that equals 2t. F prime at negative 2 equals 2 times negative 2, and that's negative 4. And let's try the other formula for the limit. And so it's usually referred to as the alternate form. So we have f prime at a is equal to the limit as x goes to a of f of a minus f of x over a minus x. So that's the formula that we created, and we can switch the order on both of them. It wouldn't matter. You could do f of x minus f of a over x minus a. It doesn't matter. All right. So we still have two functions, and we want to have two spaces for those functions. And the function is 1 over something squared. Everywhere we see an f, we put 1 over something squared, and that's what's going to be there. This is an a, and that's an x. If we substituted a right now, we would have 0 over 0, and that's why we have to do some algebra to rewrite it. So let's get a common denominator up here so that we can combine these. Let's make the denominator a squared x squared. I have to multiply this by x squared over x squared. So I'm going to multiply by x squared over x squared on that one. multiply by a squared over a squared on that one. So now we're going to have x squared over x squared a squared. Here we have a squared over x squared a squared. And that means we have x squared minus a squared over x squared a squared. And we could just have this numerator is that. And what do we do with all these denominators? Well, we can make this be we'll take the reciprocal of that and multiply by it. And we can factor this. And we can factor out a -1 here. So we have x minus a and then a minus x. Well, we need to have them in the same order with subtractions, so I'm going to factor a -1 out of this. If I distribute the -1, we'll have a negative x. -1 times negative a is positive a, so this is the same as that. And now that cancels. I'll just put that negative out in front. And now when we substitute the a, there's no more subtraction to create a indeterminate form of 0 over 0. So let's just substitute, and we'll have a plus a over a squared a squared. So x is going to a. Let's substitute the a. All right, and we can also verify that with the power rule. So if we have 1 over x squared, and we just wanted to do the derivative without a limit, f of x equals x to the -2. So instead of 1 over x squared, let's write it as x to the -2. X to the -2, that's -2x to the -3. It's just a little shorter. So we see that it's the same. All right. This one, just make sure when you're dealing with this, instead of a radical, you write it as x to the 1/2. That'll be a little easier to deal with. Should be. So, pause the video and try this one. All right, so we just copy the formula and leave a space for the first function, space for the second function, and we have 4 over something to the 1/2, 4 over something to the 1/2. instead of a radical, let's put it as a 1/2. And this will be an a, and that'll be an x. Let's get a common denominator. Here, we need to have a to the 1/2, x to the 1/2. So let's multiply this by x to the 1/2, x to the 1/2. We'll multiply this by a to the 1/2, a to the 1/2. All right, and now we have, let's take a 4 out of the numerator. And then the denominator is x to the 1/2, a to the 1/2, and let's just multiply by the reciprocal of the denominator. Since we have an x first here, let's put an x first there, and we have to do something a little creative. This is to the first power, and this is half of that power, so we can factor this into x to the 1/2 plus a to the 1/2, and then x to the 1/2 minus a to the 1/2. So this will become that, and that'll allow us to cancel. So I'm just going to copy all of this. And we have a -1 here. Let's factor that. And then we can cancel this. So we have a -4. And that'll be, let's just write it as radical x, radical a, and then radical x plus radical a. Let's substitute, replace all the x's with a's. So we'll have radical a times radical a is a, and then here we have 2 radical a. Reduce, and we have -2 over a. This is a to the 2 over 2, and this is a to the 1 over 2. If you have a to the 2 over 2 times a to the 1 over 2, you get a to the 3 over 2. And we verify with the power rule. We'll stop there.